Okay, I think we should start now. Hello everybody, welcome. This is MATLAB 101, where we're going to be teaching you how to use MATLAB for many of your ACEF projects.
Okay, so before we go into this whole workshop, I would like to have a brief introduction to some of the organizations that are really making this workshop possible. The first of these being the Alameda County Science and Engineering Fair Student Leadership Board. We are a team of 50 Bay Area high school students who work together to try and provide some support to our county science fair, basically contributing to the science fair community through outreach efforts, mentorship opportunities, and hosting various events and activities to really enrich our peers, just like today's workshop. Through these activities, we love adding a stronger sense of family to our local science fair, and we are so glad to have everyone else here to participate in today's workshop and help us accomplish our goal.
Yeah, hi everyone. The other organization making this event possible is the Reverse Engineering Foundation, and we're holding this workshop in collaboration with the ACSEF Student Leadership Board. And I'm just going to give you a brief introduction about reverse engineering, who we are, what we do. So, reverse engineering is basically a 501c3 nonprofit organization. We are a bunch of high schoolers from the Bay Area, and our goal is to teach younger students the fundamentals of electrical engineering, electronics, and how everyday electronics work. And through events like this one, we hope you gain valuable skills from the field.
And now I know we've been throwing around the word MATLAB a lot, and not a lot of you probably know what it is. It's basically a computational environment that's used for analysis of data or like numerical analysis, sometimes occasionally used for simulating and modeling. Um, for ACEF, it's relevant for projects that require the visualization of data, and it's helpful to create graphs for ACEF that are formal because MATLAB is used for most research, generally the standard when it comes to putting graphs on the trifolds, I guess you could say. And it's a programming language, and so we're going to be teaching you its syntax and everything in this workshop.
So today we're going to be teaching you MATLAB through something called kinematics. And kinematics is a subject that you probably learn, probably the first thing you learn when you start physics. So MATLAB can be used to solve these equations computationally and making and visualize the graphs really easily. So we'll start this event by going over the basics of kinematics. So what is kinematics? Kinematics is the part of physics that describes how things move without worrying about why they move. So you can think of it like this. Kinematics is a way to track motion. It tells you things like how fast something is going, how far it travels, how long it takes, and how its speed changes over time. And kinematics doesn't really care about forces, it only cares about motion and the properties of motion itself. And you see these four main kinematics equations. We only have to worry about the first three. So the first one, I'm just going to read them out. The first one is V final equals, so velocity final equals velocity initial plus acceleration times time. The second one is velocity final squared equals velocity initial squared plus 2 times acceleration times the change in position. And this can be x or y position. So it's like both the x-plane and the y-plane. And then the third equation we're concerned with is the change in the position equals the initial velocity times the time taken plus 1/2 times acceleration times time squared. So we'll go over a couple problems using these equations. So if you guys have pencils and notebooks, you can please try to work this problem out and try to see if you can use these equations to solve this problem. And by doing these problems, you'll get a basic understanding of kinematics first. And once you do these problems, we can do similar problems using MATLAB. So could everyone get to work on solving this problem? So the problem is a car starts from rest. Um, the initial velocity is 0 and accelerates at a constant rate of 5 meters per second squared. How far has the car traveled after 4 seconds? And let's just look at the answers. So I see a lot of you guys got 40 meters, and that is the correct answer. Wait, can you go to the next slide? Yeah, so for those who haven't solved it yet, this is how you solve this problem. So you basically plug in the initial velocity, the acceleration, and time into this equation, and you just solve for delta x. So it's just a plug and chug problem. Next slide. So this is the second problem we're going to be doing, and I'll do the same thing again. I'll give you a minute to solve this problem. So the problem states a cyclist is moving at 12 meters per second and hits the brakes, coming to a complete stop over a distance of 9 meters. What was the cyclist's acceleration? Good job to everyone who got -8 meters per second squared. That's the correct answer. So now we can go over the solution. Yeah, so the way you solve this problem is, the initial velocity is 12 meters per second. The final velocity is 0 because the vehicle came to a complete stop. And that the distance it took to stop or the delta x is 9 meters. So you plug these three values into the kinematics equation, vf squared equals vi squared plus 2a delta x. And you just solve for acceleration and you get -8 meters per second squared. And this is the third problem we're going to do. A model rocket is launched from rest. It accelerates upwards at 10 meters per second squared until it reaches a height of 20 meters. How much time did the flight take, and what was its final velocity at that height? And for this problem, I believe you need to use two equations to solve this problem. Yeah. So here's how you do this problem. So first, we know that the initial velocity is 0, started from rest, and the acceleration is 10 meters per second squared. Like g is approximately like -9.8, so we can approximate it to 10. And we know the delta x was 20 meters, so we plug those three values into the equation vf squared equals vi squared plus 2a delta x, and you find the final velocity, which is 20 meters per second. And then the second step, we can find time. So all you have to do is, the final velocity, and the initial velocity, and the acceleration. So you can plug those three values into the equation vf equals vi plus at to find the time of flight. And this is going to be the last problem we're doing today, and this one will require trigonometry. So the problem is a soccer ball is kicked from the ground with an initial velocity of 20 meters per second at an angle of 30 degrees above the horizontal. And so calculate the initial horizontal velocity and the vertical velocity. And using the vertical component, find the maximum height the ball reaches and assume g is -10 meters per second squared. We start by breaking down the initial velocity into its x and y components. So what does that mean? So the actual velocity is like at a diagonal. So if we use trigonometry to find like the velocity only in the x direction and the velocity only in the y direction, right? So it's like the actual velocity is the hypotenuse of a right triangle, and we're trying to find the base of the triangle. That's the x velocity. So what we do is, to find the horizontal component, we take the initial velocity v, and then we multiply by cosine of the angle. So vi times cosine theta. So that's 20 cos theta, which gives us 17.32 meters per second for the horizontal velocity. And for the vertical velocity, we do the same thing, where we use sine of the angle. So that's 20 meters per second times sine 30 degrees, which gives us 10 meters per second. So the key concept here to understand is that the horizontal velocity doesn't really matter for this problem. The vertical velocity is what we're really concerned with, is because the vertical velocity determines the maximum height of the ball, which we're trying to find, right? So even if the horizontal velocity was 0, the maximum height would still be the same. Next slide. So using the horizontal velocity that we found, the vertical velocity that we found, we can plug that into vf squared equals vi squared plus 2a delta y. And once you plug that into this equation, we know acceleration is -9.8 or -10 meters per second squared, and we know the initial y velocity. And we also know the final y velocity, because at the top, the velocity is gonna come, the ball's gonna come to a complete stop, so the velocity is gonna be 0. So if you plug those three values in and solve for delta y, we get 5 meters.
All right, I'm gonna go over MATLAB setup right now. So in MATLAb, a function
Wait,
is
one sec. Arav, aren't you gonna explain how to like set it up first?
To set it up,
Yeah, like share your screen
right
and
now,
explain.
only if you
Yeah.
want to like open your environment and follow along, then it's necessary. Otherwise, and if you do want to do that, just the link I sent in the chat, go to MATLAB Online and open it up on your browser, and you should be able to follow along that way.
So you probably want to share your screen and show them how to set up that file.
Okay, I'll show you how to do it in MATLAB Online. Just give me a sec. Okay, yeah, you first click open MATLAB Online,
Isn't
All
that
right,
it?
and then you're gonna see this basically, and then you're gonna click on New in the top left corner, New Script, yeah, and that lets you type in your script. So right now we're going over functions. So the first thing well, we're gonna go over that, but yeah, you just type it into the editor over here. Make sure your tab is on the editor tab, not any of the other tabs. Otherwise, it won't let you run it after you're done. Okay, I think we can proceed with the workshop now.
Okay, so in MATLAB, a function is essentially a block of code that performs like a specific task, right? So it uses inputs. Instead of rewriting the same code over and over, you can just put it into a function and call it whenever you need. One important thing to remember is that MATLAB is case sensitive, so a lowercase variable and an uppercase variable are not the same. You can also see that every function starts with the word function and ends with the keyword end. Inside the function is where the actual code runs, but these keywords are necessary so that you're able to actually run your program. Okay, MATLAB is especially powerful when it comes to like trig and physics, which is why it's especially used in like engineering and science. It already has like built-in constants like the value of pi and built-in trig functions such as sine and cosine. One thing to remember is that MATLAB uses radians, not degrees, so conversions are sometimes necessary. The code on this slide shows how we can calculate horizontal and vertical velocity using cosine and sine, and this is useful for real-world applications like physics problems, which you guys were just doing with Abe, and projectile motion. So to create like smooth graphs or analyze motion over time, we need many data points, right? Not just one. So the line space function allows us to generate a range of evenly spaced numbers between like a starting and ending value. For example, here we generate 150 time values from 0 to the final impact time. You might also notice like the semicolon at like the end of the line. This just prevents MATLAB from printing large amounts of data to the screen, which just helps keep your output like readable.
Yeah, if you if you actually like don't, I did this once. I forgot the semicolon, and the data set had like 1,000 values, so it just pasted 1,000 values to my editor. You don't want to do that. So yeah, that's it.
Okay, so one of the most important concepts in MATLAB is element-wise operations. So when you're working with vectors, MATLAB needs to know whether we want to operate on the entire vector at once or on each individual value inside it. By using a dot before an operator, we basically tell MATLAB to perform the calculation on every element separately. So without these dot operators, MATLAB will probably throw an error, which can lead to like incorrect results, especially when you're working with like projectile motion. Okay, finally, this slide just shows how everything comes together to create a graph. So we use a function to calculate the motion, generate time values, and compute position using formulas. Then we plot the data and customize the graph. You can adjust like the line width and like add a grid, and you can also label your axes. This is just important because when you're presenting data, like a clear graph communicates information more effectively than just like raw numbers. And yeah, that's about it.